algebra, we are moving on to CO5. Something new, Mario. Here we go. Something new, scientific notation. You may have heard it before. You've probably seen it before when using a calculator for very large or very small values. I think you should learn this in science class, but for whatever reason, it's in my standards. So here we go. Anyone know how many feet the Earth is from the sun?
26 million. Oh, it's
Still a distance from the sun. So we're not going to get into that.
Space years. 26
Space years.
Light
years?
Light years.
170. It is 491 billion feet from the sun. That's a 4, a 9, a 1, and 9 zeros.
That's like really good.
I thought it was like 4
Well,
light
I mean,
years.
it's an estimation. I mean, it's not.
I thought it was like 4 light years.
How do we know?
So how do we know? I trust the scientists for that.
I
Googled it. That's what Google told me. I don't know.
check out Google it. What's your space was it?
We're gonna write that number a second time. Make sure you all write this down in your binders. It's very important. I said so.
Numbers so important.
491 billion, and let's write it again.
Why?
491 billion. If I can do it, you can do it.
How is this?
If you were writing an essay, you might have to write 491 billion.
Yeah, we just write
491 billion times.
I'm losing a lot of ink.
I'm losing.
I have used a lot of it. That's what I care about, how much you learn about scientific notation. I'm sacrificing my own inkage for your learning.
No ink in that
Who said that?
thing. No, but in that smartboard pen.
What do you think it's writing with, Priya?
Not smartboard.
Okay,
Electronics.
all right.
Light.
So this is why we have scientific notation, okay? So that if you are in a field that you deal with very large or very small values, you don't have to actually write the entire number out, okay? So scientific notation is a way to write very large or very small values using powers of 10. That's why you learn in math class. Because really it boils down to using powers of 10. Okay? Because what happens when you multiply something by 10?
It just like moves the decimal point.
It moves the decimal to the right, right? 9 times 10 is 90 because you just move the decimal point over from 9, you put a 0 there. When you divide by 10, which way does the decimal go in a number?
That way.
To the left. Okay. Once you get that pattern down, even something like, say 45.72 divided by 10 becomes very easy. Okay. How multiplying and dividing by 10 works is that dividing by 10 moves this decimal over to the left, and your answer is 4.572. Okay. If we were multiplying by 10, it would move the decimal to the right. It'd be 457.2. Okay, so multiplying and dividing by 10 is just the decimal point moving back and forth. And that's the theory behind scientific notation. Okay, question so far? Did you all write this 491 billion down?
This is so easy.
Excellent.
Good.
Good. So, if we were to write 491 billion in scientific notation, okay, the rule for scientific notation is you get one digit, then a decimal point. Right? One non-zero digit, then a decimal point. So in 491 billion, okay, the digit that's going to be before the decimal point is the 4. Right? And then what comes after the decimal kind of depends on what the number is, okay? Every non-zero digit after the decimal gets written in as well. So the 9 and the 1, they would come after the decimal point. And then, essentially, we're going to show how many times we would multiply by 10 to get back to the original number, right? So what's happening here is in 491 billion, the decimal point's at the end. Okay? How many moves would it take? 3, 6, 9, 10, 11. 11 moves to get to where it rests now. Which means, how many times would we have to move it to get back to 491 billion? 11. Which means we would multiply by 10 11 times. Because every time you multiply by 10, it moves over once. So 4.91 times 10 to the 11th power would be 491 billion in scientific notation. Because it takes 11 tens or 11 moves to get the decimal back to the end of the original number. Follow me so far?
Yeah.
Got the gist of it? Okay. And this is really the only time in algebra that you'll see me use an X to show that we're multiplying. And I use the X here because that's what scientific notation is. When you see the word notation or notate, it means like a certain way. This is the way scientific notation is written. It's got the X to show the multiplication. It's the only time. Okay. So 5,670,000, our decimal point right now is at the end of the number here. How many movements will it take to get to 5.67? Right? So you only get one digit to the left of the point, and then all those non-zero numbers get written, everything else drops out. But how many movements does it take to get from here over to here? James? 6, right? And commas are helpful because every comma that you see is a jump of 3. So you can either count, 3, 6, right? Or just 6. But scientific notation would be 5.67 times 10 to the 6th power.
Oh, you have to do it like that.
Yes, that is how you do it. 5.67 times 10 to the 6th power. What's that? You basically keep moving until there's only one digit to the left of it. So in the next one, 878 trillion. When we write it in scientific notation, where's the decimal point going to go? Between what two values? The 8 and the 7, exactly, right? 8.78. And then how many movements does it take to get there? We can count by 3s, so we got the commas. 3, 6, 9, 12, 13, 14 moves, 14 jumps. Therefore, 8.78 times 10 to the 14th.
Okay, now I just divide.
You just, for the ones that the super small numbers, you just divide.
No, we still write it as multiplication. So we're going to learn kind of a different kind of power today. It'll keep you in suspense.
I know.
Okay. Priya?
I know a different type of power.
What is it?
You use a negative.
You do use a negative power. Spoiler alert. Very good. Okay. So in these two examples here, this positive exponent, what does it tell you about the number? If you saw 5.67 times 10 to the 6th, you see the power is a 6, you see it's positive. What does that positive power tell you about the original value? We know yet? Perfect. Well, let's talk about the next two then. Okay? So here, we're given a decimal. 0.00013 is a pretty small number. Okay? Scientific notation says there can still only be one non-zero digit to the left of our decimal, and then all other non-zero digits get written after. But in this case, instead of moving our point to the left to get there, we have to move it to the right. We have to start it here, and then 1, 2, 3, 4 hops to get it between the 1 and the 3. But if I write 1.3 times 10 to the 4th, which direction are you going to think you need to move the decimal point to get back to the original value? You're not going to know that by seeing this. It looks exactly like this, right? This number was really big. This number is really small. So, as Priya said, instead of a positive power, to show that we have to move it to the left to get it back to the original, we use a negative power. And I'll make it a little more clear here. Times 10 to the negative 4th. Okay? Which essentially means if you multiply something by 10 to the negative 4th, you're not multiplying by 10 4 times. You're dividing by 10 4 times. So a negative power is another way to write the operation of division. We'll get more to that when we get to CO13, I believe it is. Okay. For 0.0000004901, oh boy, what two numbers is the decimal point going to go between here?
4 and 9.
The 4 and the 9. Now the question is, how many hops to get it there? In this case, we do write the 0 and the 1. I said earlier that non-zero numbers got written, but because that 0 is in between the 9 and the 1, we need to include it, and the 1 as well. Okay? But to get there, let's see. 1, 2, 3, 4, 5, 6, 7. So, in scientific notation, 4.901 times 10 to the negative 7th power. Now that you've seen this, what does a positive exponent tell you about the original value? Emmeline, you're multiplying, which means your value is going to be, well, they're all positive. A negative power does not make a value negative. It just tells you which direction the point goes. But as far as the value is concerned, if your power is positive, it's going to be big. Okay? The exponent is positive because it's originally a big number. Right? In the second two, the exponent's negative. That tells you what about the value? Very small number. Okay? Small number.
Oh, water. Oh, peas.
I wrote it really small. It's a small number.
I should write the other one really big now.
Well, I didn't want to give it away. I was saving the punchline. Okay. Questions on that? You're with me so far?
Yes.
Okay. Is this new for everybody, or you're kind of? It is. Excellent. Okay. You'll impress Mr. Rohr so much. He'll be like, and scientific notation is like, we got this. Don't you worry about that. Okay. So 7.613 times 10 to the fourth. Now we're going the other way. Okay. Now you're given a value in scientific notation, and you're writing the original. So this 10 to the fourth, which direction are you moving the decimal?
Left. Right.
To the right. Because it's positive. Your number's got to get big. Okay? And how many times do you move the decimal to the right? 4. So 7.613, you move it to the right 1, 2, 3, 4 times. Uh-oh. What do you suppose goes in that empty space?
I think it's a 0.
It is a 0.
4.
Your original value was 76,130. Okay? 76,130. The exponent tells you everything. It tells you what direction and how many times to move it. Okay? So 6.8 times 10 to the 10th is going to be big. That positive power tells us that. How many times and which direction? We move 10 to the right. That positive power tells us it's to the right. The number 10 tells us 10 times. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What fills in all those empty spaces? Zeros. So we have 6, 8, and then 9 zeros.
Yes.
Put a comma every third. 68 billion is your original number. 68 billion is the original number. Okay? So far, so good?
Yeah.
All right? I'll have to erase this to give me room for the third one there. So anyone still need the notes? Okay, all right. Third one. 5.1973 times 10 to the negative 7th. Which direction are you moving the decimal, and how many times?
6. So left negative. Sorry, left 7.
Left 7 times, right? The negative power tells us it's going to the left. the 7 tells us it's 7 times. So I'm gonna have to start my number kind of over here. I'm gonna need that space to the left of it.
Oh.
And so 1, 2, 3, 4, 5, 6, 7. Didn't even erase far enough. All those empty hops, all those empty. Start over again. 1, 2, 3, 4, 5, 6, 7. All those empty spaces, including in front of the decimal, to show that we have 0 holes, right? So 0 points. 0, 0, 0, 0, 0, 0, 5, 1, 9, 7, 3.
We add another 0?
Very small. So this, you move the point to the left 7 times. That puts it here. So you've got 6 zeros to the right of the point, but because it's a decimal, you need one to the left of it also. So you essentially add a 7th 0 to show that you have no holes. Okay. 8.21 times 10 to the negative second. Which direction and how many times?
2.
2 to the left.
2 to 0.
So 8.21. 1, 2 over. I fill in that space with a 0, and I put a 0 in front of the decimal as well. Final answer. Okay.
I don't like the negative.
You need the 0 in front of the decimal just because, I mean, it's not wrong to write a decimal 0 or point 0.821, but some teachers you have in the future might require a 0 out front as well to show there are no holes. So it's just a good habit to get into.
Yeah, that's why that we don't put the 0.
You don't put the 0. You might have teachers that require you not put the 0.
He got so mad when we put the 0. He was like, "Gosh, you're not supposed to put the 0. You're wasting ink."
See? That's what I'm saying. Okay? So it's up to you. If you want to put it, put it. If you don't. I'm one that doesn't really care.
Aren't you right next to Mr. Robinson?
Yeah, it's crazy. We never hear each other though. Like, I'm not a quiet person. He can be or not be a quiet person. We never hear each other. I hear spiel all the time. It must be. So this our 4 rooms here were added onto the school probably about a decade ago or so. And so this used to be an outside wall, so it's probably thicker than just the wall separating classrooms. That's my guess. That's probably why. But yeah, this used to be an outside wall.
This used to just be a
No, I've never heard anything from that. Yeah.
So when we go into Mr. Robinson's room tomorrow.
What's that?
So when we go into Mr. Robinson's room tomorrow to grab some candy.
Yeah?
Should we just knock on the wall?
Well, no, I don't think you'd appreciate that, and I don't want to try. Like, it's not. I'm just saying I don't ever hear him.
He's out of candy.
He's out of candy. So
Yeah,
there you go. All right. Your homework for tomorrow.
You just asked.
What's that? Almost. Yeah. You've got 8 of them here to write in scientific notation. These 8 go along with the first 4 examples we did. Okay. The second set go along with the second set of 4 examples that we did. And then at the time of this document's last edit, I was about 1.2 times 10 to the 9th seconds old. How many days is that? You may use a calculator to help you. Okay. Notice your job here is not simply to convert this to scientific notation or as a number in standard form. This is how many seconds old I am. I'm asking for how many days. So once you do the conversion, you then have to convert from seconds to days. So it might behoove you to know that there are 60 seconds in a minute, right? 60 minutes in an hour, 24 hours in a day. Those are your conversion factors that you need. Sorry?
It's going to be like 12 days.
I'm older than 12 days. I can safely, I don't want to give away any answers, but that is definitely a wrong answer.
Dang it.
Okay. But good guess, James. Way to use context clues.
Would you be multiplying by 24?
You have to do several multiplications, actually. Because this gives it to you in seconds, you've got to go to days.
Isn't it division?
First, you have to get to minutes, then hours, then, well, so there are 60 seconds in a minute. There's your conversion from seconds to minutes. 60 minutes in an hour. There's your conversion from minutes to hours. 24 hours in a day. There's your conversion from hours to
Yeah.
day. Okay?
Yeah, because you're also gonna get bigger. Not.
Well, I was hoping she was going to figure it out for herself.
Yeah.
Let's let everyone embrace the struggle and enjoy the process. Okay? Any of you want to go over in the 2 minutes that we've got left? Not this one. This one you get to do solo. But any of these up here that look just way too much fun to do on your own, you want to share them with others. No? You don't want to do any together? All right, folks. Well, there you go. That's how you math.
Don't forget to like